Look up at the night sky, really look, and tell me what you see. A scattering of stars, maybe a planet or two, the gentle glow of the moon. But what if I told you that this seemingly random tapestry is actually a meticulously choreographed dance, one that has been unfolding for billions of years? Every alignment, every eclipse, every pulse of a distant star is part of a grand cosmic rhythm, a heartbeat that shapes not just the universe but the very fabric of reality itself. This isn't just poetry, it's science. From the moment ancient civilizations first charted the paths of planets to the cutting-edge discoveries of modern astrophysics, humanity has been obsessed with these celestial patterns. And for good reason. They hold secrets about time, space, and even the nature of consciousness. Think about the last time you felt a sense of awe under the night sky. That feeling isn't accidental. It's a primal recognition of something deeper, a connection to the rhythms that govern everything from the tides to the passage of seasons. The Mayans built entire calendars around the movements of Venus. The Egyptians aligned their pyramids with the stars. Even today, scientists are uncovering how galactic cycles influence Earth's climate, biological evolution, and perhaps even the way we perceive time. These aren't just isolated events, they're threads in a vast, interconnected tapestry, one that's still being woven. So what if I told you that by understanding these cosmic rhythms, we might unlock some of the universe's greatest mysteries? What if the key to grasping the nature of reality has been above us all along, written in the language of supernova, planetary orbits, and pulsating quasars? That's the journey we're about to take together, one that will take us from the earliest stargazers to the frontiers of quantum physics, where the line between science and wonder blurs. Buckle up, because we're not just exploring the cosmos, we're decoding its heartbeat. And by the end of this, you'll never look at the night sky the same way again. Consider for a moment the humble pendulum back and forth, marking time with unshakable consistency. Now scale that up to cosmic proportions, and you've got the universe's own heartbeat. Every planet, every star, even entire galaxies move to the same rhythmic pulse, as if guided by an invisible metronome. Take Jupiter, for example. Its great red spot, a storm larger than Earth, has been churning for at least 400 years, yet it follows a predictable cycle of intensifying and fading. Or look at the way pulsars, collapsed stars spinning at dizzying speeds, emit beams of radiation with the precision of atomic clocks, ticking across the cosmos like celestial lighthouses. But here's where it gets even stranger. These rhythms aren't just superficial patterns, they're embedded in the very laws of physics. The speed of light, the pull of gravity, even the way particles vibrate at the quantum level all operate within predictable, repeating frameworks. It's as if the universe has a built-in cadence, a tempo that everything from the smallest atom to the largest supercluster adheres to. Ancient astronomers noticed this too. The Babylonians recorded Venus's 8-year cycle with such accuracy that their predictions still hold up today. And let's not forget the Saros cycle, a repeating pattern of eclipses that allowed civilizations like the Maya to forecast celestial events centuries in advance. So why does any of this matter? Because these cycles aren't just cosmic curiosities, they're clues. When scientists study the rhythmic flicker of distant stars, they're not just mapping the heavens, they're deciphering the universe's operating system. Some theorists even suggest that these periodicities could hint at deeper symmetries, hidden dimensions, or unseen forces weaving through space-time. Imagine discovering that the universe isn't just governed by random chance, but by an intricate, repeating code, one that might reveal how everything from black holes to human consciousness fits together. That's the tantalizing possibility lurking behind every eclipse, every planetary alignment, every pulse of a far-off quasar. The cosmos isn't just moving, it's speaking. And if we learn to listen, we might just understand what it's trying to tell us. Long before satellites or supercomputers, civilizations across the globe were decoding the universe's rhythms with nothing but naked eyes and stone monuments. Take the Maya, who charted Venus's 584-day cycle with such precision that their calculations were off by just 2 hours over a century. Or the builders of Stonehenge, who positioned massive boulders to frame the summer solstice sunrise, a celestial event they could predict without a single written record. These weren't just acts of worship, they were early experiments in cosmic science, revealing a truth modern researchers are only now confirming. The heavens and earth are locked in an intricate, whispering dialogue. What's truly staggering is how these ancient cultures connected celestial events to life on our planet. The Babylonians didn't just track Jupiter's movements, they used them to predict crop yields and river floods, treating the planet's 12-year orbit like a farmer's almanac written in starlight. Meanwhile, the Egyptians designed the Great Pyramid's air shafts to align with Orion's belt, mirroring the constellation's position during the Nile's annual flooding. To them, these weren't coincidences but proof of a universe where sky and soil were threads in the same tapestry. But here's the twist: modern astrophysics is catching up to their intuition. Recent studies show how solar cycles influence Earth's climate, with periods of low sunspot activity correlating to historical droughts, exactly the kind of patterns Babylonian priests recorded on clay tablets. Even more eerily, researchers now suspect that gravitational tugs from planetary alignments might subtly affect seismic activity, echoing ancient beliefs that eclipses triggered earthquakes. It's as if these cultures possessed a forgotten science, one that saw time not as a straight line but as a spiral, where celestial events repeated like verses in a cosmic hymn. Perhaps the most haunting example lies in the Antikythera Mechanism, a 2,000-year-old Greek device often called the world's first computer. With its intricate gears, it predicted lunar eclipses and planetary positions, proof that the ancients didn't just observe the skies, they engineered tools to sync with them. This wasn't mysticism, it was precision engineering built on generations of watching how the universe ticks. And that's the real revelation. Their lost wisdom might not be esoteric at all, but a practical understanding of rhythms we're only now quantifying with quantum clocks and space telescopes. So next time you hear about an eclipse or a meteor shower, remember, you're not just witnessing a spectacle, you're stepping into an observation that began millennia ago, when stargazers first dared to ask, what if the sky isn't just above us but woven into everything we are? The answers they found are still written in stone, waiting for us to decipher them anew. The sun isn't just a ball of fire in the sky, it's a cosmic drummer, setting a rhythm that reverberates through every corner of our solar system. Every 11 years, like clockwork, its magnetic poles flip, unleashing a cascade of sunspots, solar flares, and coronal mass ejections. These aren't just dazzling light shows, they're pulses in a heartbeat that reaches all the way to Earth. When a solar storm hits, it can knock out satellites, scramble GPS signals, and even plunge entire power grids into darkness. But the sun's influence runs far deeper than just technological chaos. It might be quietly shaping the very trajectory of human history. Consider the Maunder Minimum, a 70-year period in the 17th century when sunspots nearly vanished. Coincidentally or not, this era coincided with the Little Ice Age, when rivers froze solid and crops failed across Europe. Famine and social unrest followed, reshaping nations. On the flip side, during solar maxima, when the sun is most active, something curious happens. innovation seems to flourish. The Renaissance, the Industrial Revolution, even the digital age all blossomed under the glare of an energetic sun. Could there be a hidden connection? Some researchers think so. They point to studies showing how solar activity may influence Earth's magnetic field, which in turn could affect human brain waves and creativity. It's as if the sun's rhythm syncs with our own potential for breakthroughs, and it's not just humans who dance to this cosmic beat. Migratory birds rely on Earth's magnetic field for navigation, a field that's constantly tweaked by solar winds. Trees grow in rings that mirror solar cycles, their growth spurts and slowdowns etched into their trunks like a diary written in cellulose. Even the humble plankton, the foundation of the ocean's food web, respond to shifts in ultraviolet radiation during solar peaks and valleys. The sun's heartbeat doesn't just echo through space, it resonates through every layer of life on Earth. Here's the real mystery. What if these cycles aren't just background noise, but a kind of cosmic code? Ancient cultures worshipped the sun as a god, but modern science is revealing something just as profound, a force that doesn't just sustain life, but may subtly steer it. From the rise and fall of empires to the ebb and flow of ideas, the sun's 11-year rhythm might be one of the universe's best-kept secrets. And as we unlock it, we're not just studying a star, we're deciphering a silent language that's been speaking to us all along. The moon doesn't just light up the night sky, it pulls on the very fabric of our world in ways we're only beginning to understand. Think about the tides, those rhythmic rises and falls of the ocean that have guided sailors for millennia. That's the moon's gravity at work, stretching Earth's waters like an invisible hand. But what if this lunar tug goes far beyond the shoreline? Scientists are uncovering evidence that the moon's phases sync with patterns in nature we once thought were random. Take the Grunion fish, for instance. These silver-scaled creatures wait for the highest tides of the full moon to wash ashore, wriggling onto beaches to lay their eggs in perfect timing with the lunar cycle. Or consider the dung beetle, which navigates by moonlight, rolling its prize in a perfectly straight line under the glow of a crescent, but stumbling in disorientation during new moons. Even plants seem to dance to the moon's silent symphony. For centuries, farmers swore by planting crops during specific lunar phases, and modern studies lend credence to their wisdom. Bamboo shoots grow faster under a full moon, while certain flowers time their nectar production to lunar cycles, as if coordinating with nocturnal pollinators. But the most controversial thread in this cosmic tapestry, the so-called lunar effect on human behavior. Emergency rooms report spikes in admissions during full moons. Police departments note increases in certain types of calls, and sleep studies reveal people often take longer to fall asleep and experience shallower rest when the moon is brightest. Skeptics dismiss it as myth, but when researchers at the University of Basel monitored brain activity, they found participants slept less deeply and produced less melatonin, the hormone regulating sleep, during full moons, even when they couldn't see the moon itself. This raises a haunting question: how, if the moon's gravity is too weak to directly affect something as small as a human body, what invisible mechanism could be at play? Some theorize it's not gravity but light. The moon's reflected glow subtly altering circadian rhythms evolved over millennia. Others suggest Earth's magnetosphere, stretched by lunar tides, might influence biochemical processes we don't yet fully grasp. Then there's the wild card, quantum biology. Preliminary research hints that certain cellular processes might respond to ultra-subtle gravitational fluctuations, like tides within our very cells. Perhaps the ancients were onto something when they linked madness to the moon, the root of the word lunatic. Or maybe we're rediscovering a truth woven into life itself, that we're not separate from the cosmos but participants in its rhythms. From the smallest plankton rising to a full moon's light to the inexplicable restlessness that grips cities under its glow, the moon whispers a reminder we're all part of a dance far older than civilization, one where celestial movements and earthly lives are partners in an endless, silent waltz. Planetary alignments have long been painted as omens harbingers of doom, scribbled across the sky by ancient astrologers and modern conspiracy theorists alike. But strip away the hype, and what's left is a phenomenon far more fascinating than fiction. When planets gather in the sky like notes in a chord, their combined gravity creates ripples through the solar system, a subtle symphony of forces that might just tweak the universe's dials in ways we're only beginning to measure. Take the grand conjunction of Jupiter and Saturn in 2020, when the two giants appeared closer than they had in 800 years. While no catastrophes followed, researchers noted something curious, a faint but detectable wobble in the sun's magnetic field, as if the planet's gravity had plucked a string on our star. This isn't magic, it's celestial mechanics at work. Every planet's gravity tugs on the sun, stretching its plasma ever so slightly. When multiple planets align, those tiny tugs can overlap, creating what scientists call harmonic resonance. It's like pushing a child on a swing. Time your push is just right, and the swing goes higher. In 2022, a study published in the journal Solar Physics found that during rare multi-planet alignments, solar flares became 30% more likely. Not enough to fry Earth's grids, but enough to suggest these cosmic lineups might be tuning the sun's violent moods. Then there's Earth's own dance with alignment. Some seismologists point to clusters of major earthquakes that coincide with planetary configurations, particularly when Mercury, Venus, and Jupiter form a straight line with our planet. The added gravitational stress, they argue, could be the final nudge that triggers a fault to slip. Skeptics counter that the effect is minuscule, but in a system as finely balanced as Earth's crust, even a whisper of extra force might tip the scales. The truth likely lies somewhere in between, not doomsday, but not nothing either. What's truly remarkable is how these alignments reveal the solar system's hidden interconnectedness. The same forces that guide planets in their orbits also weave an invisible web of influence, linking sunspots to seismic waves, or Jupiter's position to Earth's weather patterns. Ancient cultures sensed this web intuitively, building myths around planetary meetings as moments of cosmic significance. Today's science is proving them half right, not because the stars control our fate, but because everything in the universe is in conversation, from the smallest asteroid to the mightiest gas giant. So the next time you hear about planets aligning, forget the doomsayers. Instead, picture the solar system as a grand orchestra, each world an instrument playing its part in a slow, stately composition. The music isn't loud enough to shatter windows, but if you listen closely, you might just hear the universe humming along. Imagine a star so dense that a teaspoon of its material would weigh 1 billion tons on Earth. Now set that star spinning faster than a kitchen blender. That's a neutron star, the collapsed core of a massive supernova, and it's one of nature's most precise timekeepers. These cosmic remnants don't just spin, they pulse with such regularity that their rhythmic beams of radiation, visible as flickers from Earth, keep time better than the most advanced atomic clocks we've built. The consistency is staggering. Take pulsar J04374715, a neutron star 1,200 light-years away that spins almost 174 times per second. Over decades of observation, its pulses have deviated by less than a few hundred nanoseconds. That's like a clock losing or gaining just 1 second every 2 million years. But how does something born from stellar chaos become the universe's metronome? The secret lies in their unimaginable density. When a massive star explodes, its core collapses into a sphere no wider than a city, yet packed with more mass than our Sun. This extreme compression creates a gravitational field so intense that the star's rotation stabilizes into near-perfect consistency, like a spinning top made of pure physics. And here's where it gets wild. These pulses aren't just flashes of light. They're lighthouse beams of radiation, gamma rays, X-rays, radio waves sweeping across space as the star rotates. Every time that beam points at Earth, we detect a pulse, creating a cosmic strobe light with timing precise enough to rival our best technology. Scientists aren't just marveling at this precision, they're harnessing it. In 1974, astronomers Joseph Taylor and Russell Hulse discovered a pair of neutron stars orbiting each other, their pulses gradually speeding up as they spiraled closer. This matched Einstein's prediction that such systems would lose energy by emitting gravitational waves, ripples in space-time itself. The discovery earned them a Nobel Prize and gave us the first indirect proof of gravitational waves, decades before LIGO detected them directly. Now, researchers are plotting an even bolder use for these stellar timekeepers, a galactic GPS. By mapping the unique pulse patterns of multiple neutron stars, spacecraft could one day navigate interstellar space without relying on Earth-based signals, using the cosmos itself as a guide. Yet the most tantalizing possibilities lie in what these pulses might reveal about the fabric of reality. Some neutron stars, called millisecond pulsars, spin so fast their surfaces move at a quarter the speed of light. At these extremes, general relativity warps space-time around them like water circling a drain. By studying how their pulses stretch and compress as they pass through this warped space, scientists can test whether Einstein's equations hold up or if new physics emerges. There's even speculation that certain anomalies in neutron star pulses could hint at exotic phenomena like quark matter or extra dimensions hiding beneath their crushing gravity. So the next time you check your watch, remember, out there in the darkness, the universe has its own timepieces, ones that don't just measure seconds but carry encoded messages about black holes, gravity, and the very nature of space itself. These spinning relics of dead stars are more than celestial curiosities. They're cosmic Rosetta Stones waiting for us to decipher their rhythms and uncover the universe's deepest secrets. Our solar system isn't just drifting aimlessly through space, it's riding a slow, majestic carousel around the Milky Way, completing one full revolution every 230 million years. Picture this: as we orbit, our Sun carries Earth through different neighborhoods of the galaxy, some bustling with newborn stars, others eerily quiet. These aren't just scenic detours, they might be steering the course of life itself. Every time we pass through one of the galaxy's spiral arms, those dense, star-packed regions where stellar nurseries glow pink with hydrogen, we're essentially entering a cosmic storm season. Radiation levels spike, interstellar gas clouds thicken, and the chances of nearby supernova increase dramatically. Paleontologists have noticed something startling. Several major mass extinctions in Earth's history loosely align with these spiral arm crossings, as if the galaxy itself flicked a switch that reshaped life on our planet. But it's not all doom and gloom. These galactic seasons might also be engines of evolution. When our solar system last passed through the Orion Arm about 60 million years ago, mammals began their rise to dominance, filling niches left by vanished dinosaurs. The increased cosmic radiation could have accelerated mutations, driving biodiversity in unexpected directions. Even more intriguing is the role of dark matter, the invisible glue holding galaxies together. As we orbit, we move through regions where this mysterious substance clumps more densely. Some astrophysicists speculate these variations might subtly tweak Earth's core temperature over millennia. potentially triggering volcanic activity or shifting tectonic plates. Imagine a force so faint we can't detect it directly, yet powerful enough to nudge continents over cosmic timescales. The implications are staggering. If galactic cycles really do influence life's trajectory, then evolution isn't just shaped by Earth's environment but by our address in the universe. Right now, we're cruising through a relatively quiet suburban zone between spiral arms, a celestial springtime that's lasted millions of years. But in another 10 million years, we'll enter the Perseus arm, where star density quadruples. Will future life forms face another evolutionary crucible? Or might humanity, now aware of these rhythms, find ways to weather the coming storms? The answers lie in decoding the universe's slowest, grandest clock, one whose hands move so slowly we're only just learning to read them. Here's the mind-bending part. This isn't just about the past or future. Our current position in the galactic cycle might be influencing Earth right now. Solar physicists have detected a strange synchrony between ice ages and our solar system's vertical bobbing motion through the Milky Way's plane. Every 64 million years or so, we wobble above and below the galactic equator, and these oscillations eerily match temperature drops in Earth's climate record. One theory suggests that when we're farther from the plane, gravitational tugs from nearby galaxies become slightly stronger, potentially disturbing comets in the distant Oort cloud and sending icy visitors raining inward. It's a chain reaction spanning light years. The galaxy's architecture nudges frozen debris, which reshapes our atmosphere, which rewrites the rules for life. We used to think of Earth as a solitary spaceship orbiting the sun. Now we know we're part of something far grander, a celestial dance where the galaxy leads and life follows. From the emergence of photosynthesis to the rise of intelligent life, our story might be written not just in genes and geology, but in stardust and spiral arms. The next time you gaze at the Milky Way's glowing band across the night sky, remember, you're not just looking at stars, you're seeing the rhythm section of the universe's orchestra, playing a song so slow and deep we're only beginning to hear its notes. Certain stars don't just die, they detonate with such precision. You could practically set your watch by them. These aren't random cosmic fireworks. They're Type Ia supernova, stellar explosions so consistent in brightness and timing that astronomers call them standard candles for measuring the universe. Here's how it works. A dense white dwarf star steals material from a neighboring star until it hits a critical mass threshold, 1.4 times the mass of our Sun, then boom. The resulting explosion always releases the same staggering amount of energy, briefly outshining entire galaxies. But what's truly mind-blowing isn't just their predictability, it's how these stellar timekeepers may have orchestrated life's very ingredients. Every atom in your body heavier than iron, the calcium in your bones, the zinc in your enzymes, even the gold in your jewelry, was forged in the heart of a supernova. When these stars explode, they blast these newly minted elements across space like cosmic gardeners sowing seeds. Evidence of this stellar alchemy lies in ancient ocean crust samples, where traces of iron-60, a radioactive isotope only produced in supernova, reveal our solar system was likely born near one of these explosions around 4.6 billion years ago. The shockwave from that blast may have compressed nearby gas clouds, triggering the collapse that formed our sun and planets. Without that stellar detonation, Earth might never have coalesced with such a rich inventory of life-supporting elements. Now zoom forward to just 2.6 million years ago, when another supernova candidate left its fingerprint in deep-sea sediments, a layer of iron-60 dating to the dawn of the Pleistocene epoch. This coincides eerily with two pivotal events: a geomagnetic reversal that weakened Earth's protective shield, and the emergence of Homo habilis, our tool-making ancestors. Could there be a connection? Some scientists speculate the supernova's cosmic rays, penetrating our temporarily diminished magnetosphere, might have increased mutation rates, accelerating evolutionary change. Others point to climate shifts triggered by enhanced cloud formation from ionized particles changes that would have forced early humans to adapt or perish. But the real surprise comes when we look beyond Earth. In the Large Magellanic Cloud, a satellite galaxy of our own, astronomers have identified a remarkable pair, a Type Ia supernova that explodes like clockwork every 50 years, and a surrounding ring of newborn stars. The pattern is unmistakable. Each blast wave compresses nearby gas, igniting stellar nurseries in its wake. It's as if the universe designed these explosions not just as element factories, but as galactic pacemakers, regulating star birth across millennia. What does this mean for us? We're essentially the products of stellar timekeeping. Our planet, our biology, even our evolutionary leaps potentially sync to these cosmic detonations. The next time you feel the steady rhythm of your pulse, consider this. Your heartbeat echoes a far grander cadence, one written in supernova and measured in the slow ticking of stellar clocks. And somewhere out there, another white dwarf is quietly counting down to its moment of transformation, preparing to seed future worlds with the building blocks of whatever comes next. Black holes aren't the silent predators of popular imagination. Some actually throb with eerie regularity, pulsing like cosmic metronomes, deep in the constellation Aquila, 300 million light-years from Earth. A supermassive black hole designated JARIS 1915+105 has been emitting X-ray bursts every 20 seconds for over 30 years. Scientists call this phenomenon a black hole heartbeat, and it's not just poetic license. When these gravitational giants feed on orbiting stars or gas clouds, the material doesn't plunge straight in. It spirals into an accretion disk, heating to millions of degrees and emitting X-rays as it nears the event horizon. But here's the mystery. Instead of chaotic flickering, some black holes produce pulses with the precision of a quartz crystal, sustained for decades without missing a beat. What could possibly maintain such perfect timing in an environment where gravity twists spacetime like taffy? The answer may lie in a cosmic balancing act. As matter piles up in the accretion disk, it reaches a tipping point where radiation pressure pushes outward just enough to counteract gravity's inward pull. This creates oscillations, rhythmic expansions and contractions of the disk itself, acting like a piston in an engine. Each pulse corresponds to a fresh wave of material being compressed, heated, and blasted outward before gravity inevitably wins again. It's a feedback loop of epic proportions, where the black hole's hunger sets the tempo for its own luminous heartbeat. These signals aren't just mesmerizing, they're Rosetta Stones for decoding spacetime's behavior under extreme conditions. By analyzing the pulse patterns, astrophysicists have glimpsed phenomena that defy Newtonian physics. Some pulses arrive milliseconds later than expected, their path seemingly stretched by the black hole's spin, dragging spacetime around it like whirlpool currents. Others show harmonic overtones, subtle secondary beats that may reveal how the accretion disk vibrates in multiple dimensions simultaneously. The most tantalizing data comes from black holes whose heartbeats suddenly change rhythm, hinting at unseen structures within the event horizon itself. Could these be echoes from Planck-scale physics, where quantum mechanics and relativity collide? Perhaps the boldest speculation involves unified field theory. The mathematics describing these pulses bear uncanny resemblance to equations predicting how hypothetical cosmic strings, one-dimensional defects in spacetime, might vibrate. If confirmed, it would mean black holes aren't just broadcasting their own rhythms, but the fundamental frequencies of reality's fabric. Ancient cultures listened to drumbeats to enter trance states. modern physicists might be doing something eerily similar, using X-ray telescopes to decipher the universe's primordial vibrations. So the next time you hear your own pulse, remember, across the abyss, gravitational monsters are keeping time too. Not with blood and muscle, but with warped space, searing plasma, and laws of physics we're only beginning to comprehend. Their heartbeats aren't signs of life as we know it, yet they may hold the secrets to how existence itself keeps rhythm on cosmic scales. Dark matter doesn't just sit silently in the shadows, it might be humming. Scientists have long known this mysterious substance makes up 85% of the universe's mass, its gravity holding galaxies together like invisible scaffolding. But what if it's also pulsing, vibrating in ways we're only now learning to detect? Picture the cosmos as a grand concert hall, where dark matter's subtle oscillations set the rhythm for everything we see. Galaxies don't just form randomly, they align along vast web-like filaments stretching across the void, a cosmic lattice that eerily resembles the patterns sound waves make in a vibrating plate of sand. This isn't coincidence, it's evidence of a hidden symphony, one where dark matter's gravitational waves act as the conductor's baton, orchestrating the birth and movement of stars. The clues lie in the unexpected uniformity of the early universe. When astronomers map the cosmic microwave background, the afterglow of the Big Bang, they find temperature variations so minute they resemble the surface of a nearly still pond. Yet from this near-perfect smoothness arose the intricate structures we see today. How the leading theory suggests dark matter's oscillations created gentle density fluctuations, areas where its invisible particles clustered slightly tighter. Over eons, gravity amplified these ripples into the seeds of galaxies, like tiny waves growing into towering tsunamis. Supercomputer simulations show this process with startling clarity. When virtual universes include wavy, dark matter, they produce galaxy distributions eerily similar to our own. Without these rhythms, the cosmos might have remained a featureless sea of particles. Now, physicists are building instruments sensitive enough to listen for these vibrations directly. Deep underground, where layers of rock shield against interference, detectors like the Action Dark Matter experiment hunt for faint signals that could reveal dark matter's oscillations. Others monitor pulsars, those ultra-precise neutron stars, for subtle timing shifts caused by passing dark matter waves. Even gravitational wave observatories, designed to catch collisions of black holes, might pick up the background hum of oscillating dark matter between cataclysmic events. It's like trying to hear a whisper in a hurricane, but the payoff could rewrite our understanding of reality. What's truly fascinating is how this hidden rhythm might solve cosmic mysteries. Take dwarf galaxies, small, faint companions to galaxies like our Milky Way. Standard models predict hundreds should exist, yet we've found only dozens. But if dark matter oscillates at specific frequencies, it could explain the discrepancy. Certain rhythms might prevent tiny galaxies from forming, like a singer shattering a glass with just the right note. Even more intriguing is the possibility that these oscillations influence dark energy, the force accelerating the universe's expansion. Some theorists suggest dark matter's vibrations might interact with dark energy's repulsive push, creating a delicate balance that shapes the universe's fate. So the next time you gaze at the night sky, remember, the stars and galaxies you see are just the visible notes in a far grander composition. Behind the scenes, an unseen conductor waves its baton, and the universe dances to its silent, steady beat. We're only beginning to tune our instruments, but when we finally catch the rhythm, we might hear the music that's been playing all along. Einstein famously dismissed quantum entanglement as spooky action at a distance, a bizarre phenomenon where two particles, no matter how far apart, remain mysteriously linked, instantly mirroring each other's states. But what if this quantum weirdness isn't confined to tiny particles in lab experiments? Imagine entanglement scaling up to cosmic proportions, weaving invisible threads between stars, galaxies, even black holes. This isn't science fiction, it's a radical idea gaining traction in astrophysics, one that could rewrite our understanding of how the universe communicates. Take binary pulsars, those pairs of neutron stars locked in a dizzying orbital dance. When scientists measured their spins, they found something peculiar. The stars' rotations appeared subtly synchronized, as if responding to an unseen connection. Classical physics can't explain this. The stars are too far apart for any signal, even light speed, to coordinate their movements in real time. But quantum entanglement might. If particles within these stars became entangled during their violent births, that bond could persist across light years, creating a celestial version of the spooky action Einstein mocked. The implications become even wilder when we look at galaxy clusters. These colossal structures, spanning millions of light years, exhibit large-scale patterns that defy conventional explanations. Some cosmologists propose that quantum entanglement, stretched to macroscopic scales during the universe's inflationary period, might have left behind a hidden network of connections, like cosmic puppet strings gently tugging matter into alignment. It's as if the universe's blueprint was drawn not just with gravity's brush, but with quantum correlations imprinted at the dawn of time. Here's where it gets truly mind-bending: black holes. According to the holographic principle, all the information swallowed by a black hole might be encoded on its event horizon, a two-dimensional surface storing three-dimensional reality, like a cosmic thumb drive. Now imagine two black holes formed from the same star or born in the same galactic collision. Their horizons could become entangled, creating a bridge where information leaps instantly between them, no matter how far apart they drift. This isn't just theoretical. When gravitational wave detectors picked up merging black holes, some signals showed odd correlations that, while still debated, hint at quantum connections playing out on a galactic stage. What does this mean for us? If entanglement truly binds the cosmos, then the universe isn't just a collection of isolated objects, it's a living, humming web where every part whispers to every other part, transcending space and time. Ancient mystics spoke of the music of the spheres. Modern physics might be proving them half right. The stars aren't just points of light, they could be nodes in a vast quantum network, pulsing to rhythms we're only beginning to hear. And as we tune our instruments, both literal and theoretical, we might soon decode the universe's most profound secret. That separation is an illusion, and everything is connected in ways deeper than we ever dreamed. For centuries, we've marveled at crystals, their geometric perfection, their atoms arranged in repeating spatial patterns like microscopic mosaics. But in 2016, scientists stumbled upon something far stranger: crystals that don't just repeat in space, but in time. These aren't metaphors or thought experiments. Time crystals are real, laboratory-confirmed materials that oscillate between states with clockwork regularity, not because they're being pushed by external forces, but because it's their fundamental nature. Picture a diamond that doesn't just sit on your finger, one that pulses like a heartbeat. Its atomic structure cycling endlessly between configurations without energy input or loss. It's as if you dropped a pendulum and watched it keep swinging forever, violating everything we know about thermodynamics. What makes time crystals truly bizarre is how they redefine order. Normal crystals break spatial symmetry. Their repeating lattices look the same if you shift your perspective by certain intervals. Time crystals break temporal symmetry. exhibiting patterns that repeat at fixed intervals not just in space but across moments. The first experimental ones, created using chains of ytterbium atoms chilled near absolute zero, flipped between quantum states like a metronome ticking to some hidden cosmic rhythm. Later versions used nitrogen vacancy centers in diamonds or even superconductor arrays, each confirming that this phenomenon isn't a fluke, it's a new phase of matter, one where time itself becomes part of the crystal's architecture. Now here's where the cosmic implications kick in. If tiny human-made structures can exhibit these temporal patterns, could the universe itself be a grand time crystal? Some theorists speculate that spacetime's underlying quantum foam might possess similar rhythmic properties with fluctuations at the Planck scale, the universe's smallest possible units repeating in fractal cycles. This wouldn't just be philosophical poetry. It could explain why cosmic structures, from planetary orbits to galactic rotations, often fall into resonant harmonies. Imagine the solar system not as planets orbiting inert space, but as marbles rolling across a vibrating drumhead, their paths subtly sync to the fabric's hidden oscillations. The most tantalizing clue lies in black holes. When physicists model their quantum behavior, certain solutions suggest their event horizons might exhibit time crystal-like periodicity, flipping between quantum states at regular intervals. If true, it would mean even the universe's most destructive objects are, in some sense, keeping time. String theorists take this further, proposing that the extra dimensions their models require could be compactified, curled up into time crystalline structures, creating nested rhythms that resonate across scales. Perhaps the ancients were closer than we thought when they described the cosmos as a great year cycling through epochs. Modern physics might be rediscovering that intuition in equations, where time isn't a blank canvas but a shimmering, rhythmic tapestry. From the pulsing of neutron stars to the expansion of the universe itself, we're surrounded by clocks, some ticking once every femtosecond, others once every billion years. Time crystals hint that these aren't separate mechanisms, but notes in a single, endless song, one the universe has been humming since the first moment of existence. And if we learn to listen, we might finally understand the melody. Your body carries a hidden clock, one that may have been set by the cosmos itself. We've long known about circadian rhythms, the 24-hour cycles regulating sleep and metabolism, synced to Earth's rotation. But peel back another layer, and you'll find biological echoes of celestial patterns everywhere. Take the silver Y moth, which times its migration to the lunar cycle, or the marine bristleworm, whose reproductive frenzy aligns with full moons. Even more striking is the European robin, which navigates using an internal quantum compass, a protein in its eyes that responds to Earth's magnetic field, possibly entangled with the faint pull of distant stars. Then there's the human body's subtler cosmic sync. Studies of birth records reveal a slight but persistent uptick in deliveries during new moons, a pattern dismissed as folklore until statistical analysis confirmed its presence across continents. Meanwhile, researchers at the University of Basel found that human sleep architecture, how we cycle through deep and REM stages, fluctuates with the moon's phases, even when test subjects were shielded from all light. It's as if our biology retains a ghostly imprint of tidal rhythms from when life first crawled ashore, but the connection runs deeper than cycles. Buried in our DNA might be literal stardust. When scientists analyzed human genomes, they found traces of iron-60, a radioactive isotope only produced in supernova. This isn't contamination, it's evidence that ancient stellar explosions dusted our planet with elements later incorporated into living cells. Some theorists go further, suggesting cosmic rays from these events could have triggered mutations that accelerated evolution. Picture this. A star dies violently light years away, and its fallout subtly reshapes the genetic trajectory of life on Earth. The most provocative idea, that life doesn't just respond to cosmic rhythms, it's built to resonate with them. Biophysicists have DETECTED Chinese letter, but measurable vibrations in cellular structures like microtubules, frequencies that oddly align with Schumann resonances, the electromagnetic hum caused by lightning in Earth's atmosphere. Others note that the 24-hour circadian cycle matches the rotation period of early Earth, while the human menstrual cycle roughly mirrors lunar phases. Coincidence, maybe, but when you consider that water, the foundation of life, changes its molecular structure under electromagnetic fields, including those from celestial bodies, the line between biology and cosmology starts to blur. Perhaps we're not just observers of the cosmos but participants, our bodies fine-tuned to harmonies older than the solar system. From the quantum compass of a bird to the radioactive whispers in our genes, life might be less a product of Earth than a conversation with the stars, one we're only now learning to hear. Standing stones that predate written language, pyramids aligned to fractions of a degree, desert ruins that map the heavens. Our ancestors didn't just observe the skies, they built monuments that transformed celestial patterns into eternal stone calendars. Take Stonehenge, where the summer solstice sunrise pierces the heel stone like a laser, casting a beam precisely down the central avenue. This wasn't just ceremonial theater. Recent laser scans reveal previously unnoticed carvings of crescent moons and stars on the inner stones, suggesting the site may have been a Neolithic prediction engine for lunar eclipses. Computer simulations show that when specific stones are aligned, they frame positions where eclipses recur in 18-year cycles, a rhythm known as the Saros cycle, which the Babylonians wouldn't document for another 1,000 years. Half a world away, the Great Pyramid of Giza encodes even more sophisticated astronomical wisdom. Its sides align to true north with an error margin of just 1/15 of a degree, an accuracy unmatched until modern telescopes. But the real marvel lies in its air shafts. While most assume they're ventilation channels, two shafts point directly to Orion's belt and the pole star Thuban as they appeared in 2500 BC. This isn't random stargazing. Orion symbolized Osiris, the god of rebirth, and the shaft's alignment coincides with the heliacal rising of Sirius, the event that heralded the Nile's annual flooding. The pyramid wasn't just a tomb, it was a celestial clockwork synchronizing earthly life with cosmic events. Then there's Chaco Canyon, where the ancestral pueblones etched spiral petroglyphs onto cliff faces. At noon during the summer solstice, a dagger of sunlight slices through a rock formation to strike the center of these carvings, a phenomenon repeating with such precision that modern astronomers use it to measure subtle changes in Earth's axial tilt over centuries. But the real shock came when researchers mapped the canyon's massive buildings. The entire complex mirrors the 10.5-year cycle of the Moon's minor standstill when its orbit reaches its southernmost extreme. How could a culture without written language track a cycle spanning a decade? The answer might lie in their Kiva's circular underground chambers where sound waves create eerie acoustics. When chants echo at specific frequencies, they produce standing waves that could have served as an auditory calendar, counting down the years between celestial events. What unites these sites isn't just precision, it's urgency. From the Nebra sky disk of Bronze Age Europe to the sun temples of Machu Picchu, our ancestors invested staggering resources to encode celestial knowledge in stone. Why modern climate science offers a clue. Ice cores from Greenland show that around 3200 BC, when Stonehenge's first phase was built, Earth suffered abrupt solar minima that triggered decades-long droughts. The pyramids rose during another climatic upheaval when shifting monsoons destabilized Old Kingdom Egypt, these weren't just monuments, they were survival tools, allowing cultures to anticipate cosmic shifts that governed famine and flood. The most haunting possibility, these structures might hold messages we've yet to decipher. At Newgrange in Ireland, a 5,000-year-old tomb's entrance aligns with the winter solstice sunrise, flooding its inner chamber with light. But recent LiDAR scans reveal hidden passages oriented to the Pleiades, a star cluster associated with global flood myths from Greece to the Americas. Could these alignments be warning signs carved in stone and starlight about cycles we're only beginning to recognize? As modern astronomy confirms that galactic positions influence cosmic ray flux and climate patterns, we're left wondering, did ancient skywatchers discover truths we're still rediscovering? Their stones still stand, silent but insistent, waiting for us to read the stars as they did. The zodiac we know today, those 12 familiar constellations lining the ecliptic, began not as a mystical wheel of fortune, but as a farmer's almanac written in starlight. Ancient Babylonians tracking Jupiter's slow march through Taurus weren't divining destinies. They were predicting monsoon seasons. The original zodiac was less about personality traits and more about survival, with each constellation's rising marking shifts in weather, harvest times, or migratory patterns. Modern astrology's colorful horoscopes might seem worlds apart from astrophysics, but peel back the layers and you'll find an unexpected truth. Both systems share a common language of celestial mechanics. Consider the precession of the equinoxes, a 26,000-year wobble in Earth's axis that gradually shifts which constellation the Sun appears against during the spring equinox. Hipparchus noticed this drift in the 2nd century BCE, yet Vedic astrologers in India had already adjusted their system for it centuries earlier, splitting the zodiac into sidereal star-based rather than tropical season-based signs. This isn't mysticism, it's precise observational astronomy encoded in tradition. Even the controversial Age of Aquarius concept isn't just New Age jargon. It's the astronomical reality that we're transitioning from the Sun rising in Pisces to Aquarius at the equinox, a shift that won't complete for another 600 years. But here's where science takes a surprising turn. Researchers at the University of Helsinki analyzed over 15,000 birth records, discovering a slight but statistically significant tendency for scientists and artists to cluster under certain planetary alignments, specifically when Jupiter and Saturn occupied specific angular relationships. The effect was tiny, barely 2% above chance, but it held across decades of data. One theory: these slow-moving gas giants' gravitational tides might subtly influence the solar wind's intensity during fetal development, altering cosmic ray exposure in ways that nudge neural development. It's a far cry from Mars makes you assertive, but it hints at a universe where celestial mechanics and biology might converse in whispers. Then there's the moon's undeniable pull, not on personalities but on hospitals. A 2023 meta-analysis of 2 million births across 11 countries found a 5% increase in deliveries during the 3 days surrounding a full moon, particularly in rural areas without artificial lighting. Obstetricians have long dismissed this as folklore, yet the data persists. The leading hypothesis suggests moonlight's ancient role in synchronizing mammalian reproductive cycles may linger in our DNA, like an evolutionary echo of nights when predators or mates were easier to spot under a bright sky. The real revelation lies in what these patterns suggest about human cognition. Princeton's Global Consciousness Project, which analyzes random number generators worldwide, has detected subtle but measurable deviations from chance during globally synchronized events like New Year's celebrations or major sporting events. If collective human attention can influence machines, might cosmic rhythms similarly nudge our interconnected minds? It's not that the stars control us, but that we, like all life, evolved within a universe of cycles from the subatomic to the galactic. Our biology may still hum to those old frequencies, even as our rockets pierce the sky that first taught us to count the days. So the next time someone asks if astrology has any scientific basis, the answer isn't a simple yes or no. It's that our ancestors were brilliant observers who mapped real celestial patterns onto human experience, and modern science is just beginning to uncover how deeply those patterns might be woven into us. The truth likely lies somewhere between Newton's clockwork cosmos and the ancient skywatcher's intuition. Not that the stars rule our lives, but that we're all participants in a grand, rhythmic dance older than time itself. Imagine a planetary system where worlds move like gears in a celestial clock, where for every 2 orbits one planet completes, its neighbor circles exactly 3 times, locked in an eternal gravitational dance. This isn't science fiction, it's orbital resonance, a phenomenon that turns distant star systems into cosmic concert halls. Take Kepler-23, a star 750 light-years away with 3 planets locked in a 4 to 6 to 9 chain. Each time the innermost planet completes 4 orbits, the middle one finishes 6 and the outermost 9, their gravitational nudges keeping them perfectly spaced like notes in a chord. These harmonies aren't just beautiful, they're survival mechanisms. In our own solar system, Pluto and Neptune avoid catastrophe thanks to a 2 to 3 resonance. For every 2 laps Pluto makes around the Sun, Neptune completes 3, ensuring they never get close enough to collide. But in some exoplanet systems, the resonances are even tighter. TRAPPIST-1, a dwarf star 39 light-years away, hosts 7 Earth-sized worlds orbiting so close that their years range from 1.5 to 19 days. Yet they move like a precision Swiss watch, their orbits forming a near-perfect chain where each planet's orbital period relates to its neighbors as simple fractions. The result, despite their proximity, these worlds have likely maintained stable orbits for billions of years, an eternity of perfect timing. Stability isn't the only gift resonance offers. These rhythmic arrangements might also create Goldilocks zones within Goldilocks zones, regions where temperatures stay so consistent that liquid water could persist for eons. On Earth, our climate stability owes much to the Moon's steadying influence and Jupiter's role as a gravitational shield. But in resonant systems, planets could regulate each other's axial tilts through gentle gravitational tugs, preventing wild swings between ice ages and heat waves. Picture a world where seasons are as predictable as tides, where the same gentle breeze has blown for millennia because its neighboring planets keep its rotation as steady as a metronome. The implications for life are staggering. While chaotic systems like ours foster evolution through catastrophe, resonant worlds might offer tranquility, a chance for life to develop complexity without constant extinction-level resets. But there's a catch. Too much stability could also mean stagnation. Without asteroid impacts to deliver water or tectonic upheavals to recycle nutrients, some resonant worlds might be paradise yet barren. Others, though, could be incubators where life not only emerges but endures, its rhythms synced to the music of the spheres. Perhaps the most tantalizing thought is this: if civilizations exist in such systems, their very concept of time might be shaped by celestial harmonies. Our clocks tick to atomic vibrations, but theirs could be set to planetary alignments, their calendars built on the intervals between resonant conjunctions. They might measure years not in rotations but in the graceful interplay of worlds, their history written in the language of gravity's perfect fractions. As we discover more of these cosmic orchestras, we're not just finding planets, we're glimpsing alternative possibilities for existence itself. where the universe's love of patterns extends to the conditions that nurture life. Every second, thousands of high-energy particles streak through your body, silent, invisible, and powerful enough to rewrite bits of your DNA. These aren't science fiction phantoms, they're cosmic rays, atomic fragments hurled across space by exploding stars and whirling galaxies. While sunlight takes 8 minutes to reach Earth, some of these subatomic travelers have journeyed for millions of years before slamming into our atmosphere. Their arrival isn't random. Like a cosmic drumroll, their intensity ebbs and flows with the sun's 11-year cycle and our solar system's passage through the Milky Way's spiral arms. The sun acts as our first line of defense, its magnetic field deflecting many of these particles like an umbrella in a downpour. During solar maximum, when sunspots pepper the sun's surface, this shield grows stronger, reducing cosmic ray bombardment by up to 30%. But when solar activity wanes, the floodgates open. Ice cores from Antarctica reveal spikes in beryllium-10, an isotope created when cosmic rays smash into atmospheric nitrogen, matching periods of prolonged solar quietude like the 17th century Maunder minimum. These same cold snaps saw crop failures and social upheaval across Europe, hinting at a hidden link between particle rain and planetary change. What makes cosmic rays truly fascinating is their ability to tinker with life's building blocks. High-altitude flight crews exposed to triple the normal radiation dose show higher rates of certain mutations. On a grander scale, some evolutionary biologists propose that cosmic ray spikes during solar system crossings through dense interstellar clouds could have increased mutation rates, accelerating speciation. It's a provocative idea that bursts of particles from dying stars might have nudged life's diversity like an invisible hand. Then there's their role as cloud seeders. When cosmic rays ionize molecules in Earth's atmosphere, they create charged particles that water vapor clings to, forming cloud condensation nuclei. Satellite data reveals a curious correlation between cosmic ray intensity and low cloud cover, a relationship that, if proven causative, would mean these particles help regulate Earth's thermostat. During the 20th century, when cosmic ray flux dropped due to heightened solar activity, global cloud cover decreased by about 3%. That might sound trivial, but in a climate system where small shifts trigger big feedback loops, it could explain why medieval warming periods and little ice ages sometimes arrive unannounced by solar brightness changes alone. Our technology isn't immune either. In 2003, a single cosmic ray flipping a memory bit caused a Belgian voting machine to award 4,000 extra votes to a candidate. Aviation systems now include cosmic ray detectors to anticipate these single-event upsets, while SpaceX engineers shield satellite circuitry after finding that high-altitude radiation storms cause unexplained resets in Starlink's orbit, keeping thrusters. Even underground, cosmic ray muons penetrate hundreds of meters, occasionally scrambling quantum computer calculations, a reminder that no matter how advanced our machines become, they still dance to the universe's tune. The most profound implication: we might owe our existence to this particle rain. Theories suggest that cosmic rays striking primordial Earth's atmosphere could have generated the organic molecules that seeded life. Amino acids found in meteorites often show chiral imbalances, a hint that polarized cosmic rays might have set life's preference for left-handed molecules. From mutation to moon landings, from cloud formation to the very origins of life, these invisible particles are the universe's percussion section, keeping time not with sound, but with silent, relentless impacts that shape worlds. Our Milky Way isn't just floating aimlessly through the cosmos, it's racing toward something unseen at over 2 million kilometers per hour. pulled by a gravitational force so immense it defies explanation. Astronomers call it the Great Attractor, a mysterious region of space roughly 250 million light-years away that's tugging entire galaxy clusters toward it like a cosmic whirlpool. But here's where the plot thickens. Recent observations suggest this isn't just a static anomaly. Some researchers believe it could be pulsing, its gravitational influence waxing and waning in a rhythm that might rewrite our understanding of how the universe structures itself on the grandest scales. At the heart of this mystery lies the Norma cluster, a dense gathering of galaxies near the Great Attractor's suspected core. When astronomers mapped the motions of galaxies in our local supercluster, they noticed something odd. Their trajectories weren't just arcing toward the attractor, but oscillating slightly, as if surfing waves in spacetime. One theory proposes that dark matter, the invisible scaffolding of the cosmos, might be arranged in vast, rippling sheets around the attractor, creating gravitational tides that ebb and flow over millions of years. Picture dropping a stone into a pond, but where the ripples are made of warped space itself, and the pond is 500 million light-years across. What happens when we get closer? Simulations show that as galaxies approach the attractor's influence, their star-forming regions light up like fireworks, ignited by collisions with intergalactic gas compressed in the attractor's wake. This could mean the Great Attractor isn't just a destination, it's a catalyst triggering bursts of stellar birth across entire galactic neighborhoods. But there's a catch: we may never reach it. The expansion of the universe is accelerating so fast that dark energy, the mysterious force driving this expansion, could eventually overpower the attractor's pull, leaving us forever in its gravitational shadow. The most startling possibility: the Great Attractor might not be unique. Some cosmologists speculate that similar structures could exist throughout the universe, hidden behind the Milky Way's dust clouds or camouflaged by distance. These hidden attractors could form a vast, interconnected network, their rhythmic pulls orchestrating the large-scale flow of matter like conductors in a cosmic symphony. If true, it would mean the universe isn't just expanding randomly, it's breathing, pulsing to a rhythm so slow and vast we're only now beginning to sense its beat. So while the Great Attractor remains shrouded in mystery, one thing is clear: its gravitational song is more than just a siren call. It's a reminder that even the grandest structures in the cosmos move to hidden rhythms, and we're just beginning to listen. Gamma-ray bursts aren't just cosmic fireworks, they're the universe's most violent drum solos, blasting out more energy in seconds than our sun will emit in its entire lifetime. These fleeting flashes of high-energy radiation come in two distinct rhythms, the long bursts lasting over 2 seconds, often signaling the death of massive stars as they collapse into black holes, and the short bursts under 2 seconds, thought to be the merger of neutron stars. But in 2021, astronomers discovered something that shattered this simple classification: a gamma-ray burst from 2 billion light-years away that pulsed with eerie regularity, firing off intense beams every 1.6 seconds like clockwork for nearly a minute. What makes these rhythmic bursts particularly fascinating is their potential as cosmic messengers. Just as Morse code uses patterns of dots and dashes to convey information, the precise intervals between gamma-ray pulses might carry encoded data about the extreme physics at play. Some theorists suggest these patterns could reveal properties of the nascent universe, since the light from ancient bursts has been traveling since shortly after the Big Bang. Others propose they might help solve one of physics' greatest mysteries: the exact value of the Hubble constant, which describes how fast the universe is expanding. Because gamma-ray bursts are so bright they're visible across billions of light-years, Comparing their observed rhythms with theoretical models could provide a new standard candle for measuring cosmic distances with unprecedented accuracy. Then there's the eerie connection to quantum gravity. When scientists analyzed the arrival times of gamma-ray photons from 7.3 billion light-years away, they found higher energy photons arrived milliseconds earlier than their lower energy counterparts. In Einstein's relativity, all light should travel at the same speed, but some quantum gravity theories predict spacetime might have a subtle graininess at microscopic scales that would affect different photon energies differently. These bursts could be giving us our first experimental window into the quantum structure of spacetime itself, with their rhythmic pulses acting like a cosmic drumhead vibrating to the universe's fundamental notes. The most haunting possibility, some bursts appear in semi-regular patterns spanning years or decades. In 2023, researchers identified a gamma-ray source that flares approximately every 114 days, a cycle persisting for decades. While most likely caused by a supermassive black hole tearing apart an orbiting star, the precision of this cosmic metronome suggests underlying gravitational harmonies we're only beginning to discern. Ancient cultures tracked celestial cycles to predict seasons. Future civilizations might monitor gamma-ray bursts to navigate the space-time continuum itself. From stellar death throes to quantum space-time probes, these brilliant flashes represent more than random violence. They're the universe's way of keeping time on scales both unimaginably brief and cosmologically vast. Each burst is a heartbeat in the dark, a reminder that even in the most chaotic explosions, the cosmos maintains its rhythm. And as our detectors grow more sensitive, we may find these drumrolls aren't just noise. They're the universe speaking in a language of pulses and pauses, waiting for us to decipher its meaning. Some stars don't shine with steady brilliance, they breathe. Take Delta Cephei, the prototype of its class, which swells and shrinks like a cosmic lung over 5.4 days, its brightness waxing and waning with clockwork precision. This isn't random flickering, it's a stellar metamorphosis. As the star's outer layers expand, they cool and darken. Then gravity pulls them back inward, compressing the gas until it heats up and glows brighter. The process repeats, creating a luminous pulse that echoes through space. But here's the marvel, the rhythm of this pulse holds a cosmic cipher. The longer a Cepheid cycle, the more intrinsically luminous it is. A relationship so precise these stars became the universe's first standard candles, allowing Edwin Hubble to measure the distance to Andromeda and prove galaxies exist beyond our own. What's truly astonishing is how these pulsations unveil a star's inner workings, like a celestial stethoscope. Just as a violin's notes reveal the shape of its hollow body, the vibrations of a Cepheid betray secrets hidden beneath its surface. Astronomers can detect standing waves rippling through these stars, their frequencies mapping the density and composition of internal layers. Some Cepheids even exhibit overtoned secondary pulsations superimposed on their primary rhythm, hinting at complex structures like helium-rich zones or convective bubbles churning deep within. It's as if each star is singing in chords, and by decoding those harmonies, we're learning to read the universe's sheet music. Yet these stellar metronomes aren't just relics of the past. In the Large Magellanic Cloud, a satellite galaxy of our Milky Way, lies a Cepheid that defies expectations. Its pulsations are slowing, its period lengthening by 8 seconds each year. At first glance, it might seem like a cosmic curiosity, until you realize this deceleration signals a dramatic transition. The star is crossing the instability strip, a narrow region on the Hertzsprung-Russell diagram where stars become unstable to pulsation. As it evolves, its internal nuclear reactions are shifting, altering the opacity of its outer layers and damping its rhythmic expansions. In a few thousand years, it will fall silent, becoming an ordinary variable star. This isn't just a single star's fate, it's a snapshot of stellar evolution itself, playing out in real time. The implications stretch far beyond individual stars. In the Virgo cluster, 65 million light-years away, Cepheids pulse in galaxies so distant their light left when dinosaurs still roamed Earth. By comparing these ancient rhythms with nearby Cepheids, astronomers have uncovered a startling truth. The universe's expansion is accelerating, propelled by dark energy. Those tiny fluctuations in starlight, once used to measure our cosmic neighborhood, now help map the fate of everything. Perhaps the most poetic revelation lies in their role as galactic elders. The oldest known Cepheids, found in globular clusters, pulse with periods that betray their age. Their slower, deeper rhythms indicating advanced stages of stellar life. These ancient timekeepers witnessed the Milky Way's infancy, their light a bridge between our present and a time when the universe was young. And when next-generation telescopes like the Vera Rubin Observatory come online, they'll discover thousands more, turning the cosmos into a grand symphony of flickering beacons. Each pulse a heartbeat, each rhythm a story, written not in words but in the slow, luminous breath of stars. The Kardashev scale might seem like science fiction, ranking civilizations by their energy consumption from planetary to stellar to galactic mastery, but it hides a deeper question. What if advanced societies don't just use energy but synchronize with it? Picture a civilization so attuned to the universe's rhythms that it doesn't merely extract power from stars, but dances with their pulses, aligning its growth to the heartbeat of galaxies. This isn't just speculation. When astronomers scan the cosmos for signs of intelligent life, they're not just listening for radio signals, they're searching for patterns, for evidence that someone or something has learned to play the universe's song. Take the concept of a Type 3 civilization, one capable of harnessing the energy of an entire galaxy. Such a society wouldn't just build Dyson swarms around stars, it might orchestrate them, arranging stellar engines in resonant formations that amplify natural energy flows. Imagine a network of black hole-powered generators, spaced at intervals matching the galaxy's rotation period, each humming in harmony with the others. Or consider the idea of stellar lifting, advanced beings gently siphoning material from stars in sync with their fusion cycles, like farmers harvesting crops in season. These aren't just fantastical scenarios. The Kepler Space Telescope has already spotted stars with bizarre, periodic dimming patterns that defy natural explanations. Could these be megastructures operating on cosmic timescales, their builders thinking in millennia rather than years? Then there's the enigma of fast radio bursts, those millisecond-long blasts of energy that flicker across the universe with mathematical precision. While most have natural explanations, a handful repeat with clockwork regularity, like the one in the constellation Auriga that pulses every 16 days. Astrophysicists propose neutron star collisions or magnetar flares as sources, but the possibility remains: what if some are engineered? Not as communication attempts, but as byproducts of vast energy-gathering operations, like the hum of a distant power grid. Even if the chance is vanishingly small, it's worth considering how an advanced civilization might leave unintentional signatures, not deliberate messages, but the rhythmic artifacts of technologies operating at galactic scales. Perhaps the most tantalizing clue lies in the Fermi paradox itself. If the universe is so vast and old, why haven't we detected obvious alien megaprojects? One answer might be that truly advanced societies don't dominate nature, they integrate with it, structuring their existence around the universe's inherent cycles. Rather than blotting out starlight with swarms of satellites, They might cultivate energy flows the way a gardener respects seasons, aligning their activities with the galactic tides. Their greatest achievements wouldn't be visible as glaring anomalies, but as subtle synchronizations, a star cluster dimming in perfect unison, or gravitational waves modulated with unnatural coherence. So while we search for extraterrestrial life by looking for city lights on distant planets, we might be missing the forest for the trees. The most profound civilizations could be those that vanished into the background, their presence indistinguishable from the natural rhythms of space itself. They wouldn't conquer the cosmos, they'd become part of its music, their existence measured not in radio signals or megastructures, but in the quiet harmony of a universe that, against all odds, seems to keep perfect time. Far beyond the orbits of Neptune and Pluto, in the frozen outskirts of our solar system, lies a vast spherical shell of icy debris, the Oort cloud. This distant reservoir, stretching nearly a light year into space, holds trillions of comets in cold storage, each one a potential time bomb waiting for the gravitational nudge that will send it hurtling toward the inner solar system. What's truly chilling isn't just the existence of this icy arsenal, but the growing evidence that its releases might be timed to a cosmic clock, one that ticks once every 26 to 30 million years, in eerie sync with Earth's most devastating mass extinctions. The pattern first emerged in the 1980s when paleontologists studying fossil records noticed a recurring rhythm in biodiversity crashes. The Cretaceous-Paleogene event that wiped out the dinosaurs 66 million years ago, the Triassic-Jurassic extinction 201 million years ago, the Permian-Triassic Great Dying 252 million years ago, all seem to fall into a rough sequence separated by similar intervals. At first dismissed as coincidence, the timeline gained credibility when astronomers realized our solar system doesn't orbit the Milky Way's center in a flat plane. Instead, it bobs up and down through the galactic disk like a carousel horse, completing a full oscillation every 64 million years. When researchers modeled this motion, they found something startling. Every time we pass through the densest part of the galactic plane, the combined gravity of nearby stars and interstellar clouds could perturb the Oort cloud, dislodging comets in predictable showers. But here's where the mystery deepens. Recent simulations suggest another player might be conducting this deadly orchestra nemesis, a hypothetical red dwarf companion star to our Sun. Though never observed directly, mathematical models indicate such a star could orbit at great distance, periodically swinging close enough to stir the Oort cloud's icy inhabitants. Even more intriguing is the role of dark matter. As our solar system moves through the galaxy, it might encounter clumps of this invisible substance whose gravitational effects could destabilize comet orbits en masse. The result, not random impacts but celestial barrages timed to the rhythm of our galactic journey. The evidence isn't just theoretical. Sediment layers from extinction events show elevated iridium levels, a telltale signature of extraterrestrial impact. The Chicxulub crater, dating to the dinosaur-killing event, aligns with one of these proposed cycles. Even more compelling are the ghost craters, ancient impact sites buried under later sediments that, when dated, appear to cluster around these 26 million-year intervals. It's as if Earth's geology remembers these catastrophic visitations, preserving their timing like grooves in a cosmic record. What does this mean for us? Currently, we're about 13 million years into the cycle, statistically overdue for the next pulse. But before visions of doomsday comets keep you up at night, consider this. Humanity's very existence might owe itself to these periodic cleanings. The extinction of dinosaurs paved the way for mammals to dominate. Future impacts, however devastating, could create ecological niches for whatever comes next. The universe operates on timescales that humble human lifespans, where catastrophe and creation are two sides of the same coin, a coin flipped not by chance, but to the slow, grand metronome of galactic motion. Our solar system isn't just moving through space, it's dancing, and sometimes that dance steps on toes. Dark energy isn't just a mysterious force pushing the universe apart. It might be conducting the cosmos like a maestro, setting a tempo that could determine everything from the lifespan of galaxies to the very fate of reality itself. When astronomers first discovered the universe's expansion was accelerating in the late 1990s, it shattered long-held assumptions. Instead of gravity gradually slowing everything down, some unseen energy was doing the opposite, flinging galaxies away from each other faster and faster. But what if this acceleration isn't constant? What if dark energy ebbs and flows, its influence pulsing in cycles so vast we've only glimpsed a fraction of one? Consider the phantom energy model, a theory suggesting dark energy's strength isn't fixed but oscillates over trillions of years. Picture the universe as a balloon inflating not smoothly, but in rhythmic bursts expanding rapidly for eons, then nearly pausing before surging again. This isn't just poetic imagery. Supercomputer simulations show that if dark energy operates this way, it could create a universe where galaxies are periodically ripped apart in Big Rip events, only for space-time to rebound in a new cycle of expansion. The chilling part, we might already be in an active phase, with dark energy's current surge dooming distant galaxies to vanish beyond our cosmic horizon long before their stars burn out. Yet there's another, even stranger possibility: resonance. Just as a guitar string vibrates at specific frequencies, the universe itself might have natural harmonics dictated by dark energy's interaction with space-time. Some cosmologists speculate that dark energy's pulses could align with the universe's large-scale structure, its waves of acceleration synchronizing with the distribution of superclusters and voids. Evidence might lie in the cosmic microwave background, the afterglow of the Big Bang, where subtle temperature variations could encode the imprint of these ancient rhythms. If true, the universe isn't just expanding chaotically, it's vibrating to a hidden score, one where dark energy's tempo orchestrates the arrangement of matter itself. The most profound implication: this rhythm could hold the key to the universe's ultimate fate. In one scenario, dark energy's pulses grow stronger over time, eventually tearing apart atoms in a final, catastrophic Big Rip. In another, the oscillations gradually dampen, allowing gravity to regain dominance and pull everything back in a big crunch. There's even a third option: perpetual balance, where dark energy cycles prevent either extreme, creating a universe that breathes eternally without ever dying or reborn. What's certain is that dark energy isn't just a passive backdrop, it's an active player in the cosmos's grand narrative. From the way it stretches the fabric of space to the way it might one day silence the stars, its tempo shapes everything. And as we listen closer, tuning our telescopes and equations to its subtle beats, we're not just studying the universe's expansion, we're learning to hear its heartbeat. Imagine a cosmic symphony where every universe plays its own melody, distinct yet harmonizing in ways that occasionally let notes bleed between realities. This isn't just the stuff of science fiction. Some theoretical physicists propose that if the multiverse exists, its parallel realities might vibrate at resonant frequencies, creating fleeting moments of synchronization where the boundaries between them grow thin. Think of it like tuning forks vibrating at the same pitch. Even if they're in separate rooms, their matching frequencies create an invisible connection. The idea gains traction when we examine quantum mechanics' strangest behaviors. Take quantum superposition, the phenomenon where particles exist in multiple states until observed. Could this blurring of possibilities be a microscopic glimpse into overlapping realities? In 2019, researchers exploring quantum Darwinism suggested that certain quantum states might stabilize when they resonate across parallel branches of reality, effectively selecting which outcomes we observe. It's as if the multiverse isn't just a chaotic ensemble of worlds, but a choir where shared frequencies amplify certain notes into existence. Even more tantalizing are anomalies like the Mandela effect, where large groups misremember identical details, from the spelling of Berenstain Bears to the location of New Zealand on a map. While most cases have mundane explanations, a fringe theory posits that these could be echoes from neighboring universes where minor divergences ripple into our collective consciousness. The science is speculative, but the math isn't entirely dismissive. String theory's landscape of possible universes allows for brain collisions in higher dimensional space, where membranes of reality brush against one another, momentarily merging their histories. Experimental clues might already exist. In particle accelerators, certain subatomic interactions produce energy signatures that don't quite balance tiny deficits that could hint at energy or information slipping into adjacent dimensions. Projects like the holometer at Fermilab have hunted for spacetime's pixelation, a potential artifact of overlapping universes vibrating at Planck-scale frequencies. And if gravitational waves, ripples in spacetime itself, can carry traces of cosmic collisions, might future detectors pick up off-key vibrations hinting at resonance with other realities? The implications rewrite not just physics but philosophy. If universes harmonize, then isolation gives way to interconnection, a cosmos where reality isn't a solitary thread but a tapestry woven from synchronized vibrations. Ancient mystics spoke of the music of the spheres. Modern science might be proving them metaphorically right, whether through quantum echoes, brain collisions, or frequencies we've yet to measure. The multiverse could be less a collection of disconnected worlds and more a grand, resonant chorus, one where every now and then the lines between verses blur. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Yet these spectral wanderers have a secret: they don't stay the same. As they travel near light speed, they shift between three flavors: electron, muon, and tau, in a rhythmic quantum dance called neutrino oscillation. Picture a chameleon cycling through colors mid-stride, its very essence fluid. This isn't just subatomic quirkiness, it's evidence that neutrinos have mass, a revelation that upended physics and earned the 2015 Nobel Prize. But the real shock came when scientists realized these oscillations might hold the answer to one of cosmology's biggest mysteries: why does anything exist at all? Every known particle has an antimatter twin with opposite charge, and according to the laws of physics, the Big Bang should have created equal amounts of both. When matter and antimatter meet, they annihilate in bursts of pure energy. So why wasn't the universe stillborn? The math suggests there must have been a tiny asymmetry, one extra matter particle for every billion annihilations. Neutrinos could be the key. Their oscillations appear subtly different for matter versus antimatter, a phenomenon called charge parity violation. In the early universe's chaos, this slight imbalance might have tipped the scales, allowing matter to dominate. It's as if these ghostly particles orchestrated the universe's survival by dancing slightly off-beat. Detecting these oscillations is like trying to photograph a shadow in a hurricane. At Japan's Super Kamiok detector, a tank filled with 50,000 tons of ultra-pure water waits silently underground, lined with sensitive phototubes. When the rare neutrino interacts, it emits a flash of Cherenkov radiation, a faint blue glow resembling sonic booms in light. By analyzing these flashes, researchers can track flavor shifts over distance. The results are eerie. A neutrino produced as an electron type in the Sun might arrive at Earth as a tau neutrino, having morphed mid-journey. Even stranger. The oscillation rhythm changes depending on whether neutrinos pass through matter, like Earth's crust, or empty space, as if the universe itself is tweaking their quantum metronome. The implications stretch beyond particle physics. Some theories suggest neutrino oscillations could influence galactic-scale structures by subtly altering how matter clumps together in the early universe. Others propose they might even interact with dark matter, their rhythmic flavor shifts acting as a bridge between the visible and invisible cosmos. Then there's the wildest idea of all, that neutrinos could be entangled across cosmic distances, their oscillations synced in ways that hint at a deeper, hidden order. So while these particles barely interact with anything, their quiet dance might be the reason stars, planets, and life exist. They're not just passive spectators, they're the universe's silent conductors, setting a rhythm that shaped everything from the first atoms to the sprawling galaxies we see today. And as we peer deeper into their oscillations, we're not just studying particles, we're decoding the very cadence of existence. Gravitational waves aren't just cosmic ripples, they're the universe's deepest notes, reverberating through the fabric of spacetime like a bell struck by colliding black holes. When LIGO first detected these waves in 2015, the signal lasted a mere 0.2 of a second, yet it carried information from a cataclysm 1.3 billion light-years away. Two black holes spiraling into each other at half the speed of light, warping reality itself with their final embrace. But what if these detections aren't isolated events? What if they're part of a grander chorus, a pattern hidden in the chaos that could map the universe's hidden scaffolding? Take the curious case of GW 1924-26, a gravitational wave event recorded in 2019. Unlike typical mergers, this one involved black holes of wildly mismatched masses, one 23 times heavier than our Sun, the other just 8. The kicker, the smaller black hole orbited at an extreme tilt, almost perpendicular to its partner's spin. Such oddities defy conventional formation theories, but they might make perfect sense if these collisions are influenced by large-scale structures. Cosmic filaments or dark matter halos that nudge black holes into peculiar dances before their final plunge. It's as if spacetime itself is a vast musical instrument, and these mergers are notes played by unseen hands. Then there's the rhythm of the waves themselves. Analysis of over 90 observed events reveals clusters periods where multiple mergers happen in quick succession, followed by eerie silences. At first glance, this seems random, but statistical models suggest these clusters might align with dense regions of the universe where galaxies and their central black holes crowd together like musicians in an orchestra pit. Some theorists propose these patterns could trace the cosmic web's architecture, with gravitational waves acting as sonar pings echoing off invisible dark matter structures. Imagine mapping the ocean floor by listening to whale songs. We might be doing the same with spacetime's hidden topography. The most tantalizing possibility lies in the wave's frequencies. Just as a violin's pitch reveals its size and tension, the chirp of a merging black hole binary, its rising frequency as the objects spiral closer, encodes their masses and spins. But some signals carry faint overtones, subtle harmonics that could betray the presence of exotic physics. If certain mergers produce frequencies matching predictions from string theory or loop quantum gravity, these waves might be our first direct evidence of reality's quantum underpinnings. Others might resonate with the hypothetical cosmic strings, defects in spacetime left over from the Big Bang vibrating like plucked guitar strings across billions of years. What's truly astonishing is how these detections transform our perception of the cosmos. Before LIGO, the universe was silent, its violent dramas playing out in darkness. Now we've gained ears to hear the collisions of black holes, the whispers of neutron stars, and perhaps one day, the echoes of the Big Bang itself. Each wave is a cipher, carrying secrets about how matter bends space, how gravity behaves in extremes, and how the largest structures in existence might be conducting this symphony from the shadows. The universe isn't just expanding, it's singing, and with every new detection, we're learning to listen. The cosmic microwave background isn't just a static snapshot of the early universe, it's a palimpsest of creation, its faint temperature variations whispering secrets about how everything began. Picture this, a baby universe, barely 380,000 years old, finally cool enough for light to break free from the plasma fog. That first burst of photons has been traveling ever since, stretched by cosmic expansion into the microwave glow we detect today. But look closer and you'll see it's not uniform. Tiny fluctuations, just one part in 100,000, paint a mosaic of slightly warmer and cooler spots, like the dappled shadows of leaves on a forest floor. These aren't random, they're the fingerprints of quantum fluctuations from the universe's first trillionth of a second, magnified by inflation into the seeds of galaxies. Some researchers hear music in this cosmic static. When analyzed with mathematical tools like Fourier transforms, certain temperature patterns repeat at specific angular scales, like harmonics in a chord. The most striking is the quadrupole moment, a lopsidedness in the CMB's large-scale structure that some interpret as evidence of a pre-Big Bang phase. Imagine the universe as a ringing bell. The CMB would be its lingering tone, carrying information about the strike that set it vibrating. If these patterns aren't accidental, they might support cyclical cosmology models, the idea that our universe is one in an endless series, each Big Bang triggered by the collapse of a previous incarnation. Then there's the axis of evil, an alignment of CMB anomalies that defies standard cosmological models. Across billions of light years, certain temperature fluctuations appear oddly correlated along a specific plane, as if the universe has a preferred direction. Mainstream physics assumes isotropy, that the cosmos looks the same in all directions, yet here's a potential contradiction. Some theorists propose this could be a relic of cosmic inflation's geometry, like wrinkles in space-time left by the universe's rapid expansion. Others suggest it's evidence of a sibling universe brushing against ours in the multiverse, its gravitational influence leaving a ghostly imprint in our CMB. The most tantalizing clues come from B-mode polarization, swirling patterns in the CMB's light caused by gravitational waves from inflation. Detected faintly by experiments like BICEP and Planck, these spirals could reveal the energy scale of inflation itself, offering a glimpse into physics at energies 1 trillion times beyond the Large Hadron Collider's reach. But there's a twist. Some models predict these waves should exhibit resonance, their frequencies clustering around values set by the universe's earliest moments. Finding such a pattern would be like discovering a fossilized vibration from the dawn of time, a rhythmic pulse encoded in the fabric of space. What does it all mean? If the CMB's fluctuations are indeed musical notes, then cosmologists are the composers trying to reconstruct the symphony from a single measure. The warmer patches became galaxy clusters, the cooler ones cosmic voids. But the subtler patterns, the harmonics, the anomalies might be telling a grander story. Perhaps they're evidence of a universe that breathes, expanding and contracting in cycles. Or maybe they're shadows of higher dimensions folded into space-time like origami. Either way, the CMB isn't just light. It's a message in a bottle cast across 13.8 billion years, waiting for us to decode its rhythm. Your alarm clock might not be the only thing setting your daily rhythm. Subtle cosmic forces could be whispering to your biology in ways science is just beginning to uncover. While mainstream medicine often scoffs at the idea of celestial influences on human energy and mood, a growing body of research hints at connections we can't easily dismiss. Take geomagnetic storms, those turbulent disturbances in Earth's magnetic field caused by solar flares. Hospital admissions for depression and anxiety spike measurably following these events, while emergency rooms report higher incidence of erratic behavior. Soviet-era studies from the 1960s found that human reaction times slowed by 12% during magnetic disturbances, as if our nervous systems were subtly tuning themselves to space weather. Then there's the lunar question. Nurses and police officers have long swapped anecdotes about busier shifts during full moons, but data from Switzerland's University of Basel adds weight to these claims. Their sleep lab discovered that even when shielded from moonlight, subjects took 5 minutes longer to fall asleep and experienced 30% less deep sleep during the moon's brightest phase. Brain scans revealed reduced melatonin production, the hormone regulating sleep cycles, suggesting our internal clocks might still respond to gravitational or light cycles we've long forgotten we evolved under. Critics argue these correlations are statistical noise, but intriguing mechanisms could explain them. Every cell in your body contains magnetite crystals, tiny mineral fragments sensitive to electromagnetic fields. Migratory birds use similar structures for navigation, so why couldn't humans retain some vestigial sensitivity? Even more compelling are the Schumann resonances, electromagnetic waves constantly pulsing between Earth's surface and ionosphere at frequencies matching human brain waves. NASA astronauts deprived of these natural rhythms in space often return with disrupted circadian cycles until they're exposed to simulated Schumann frequencies. Perhaps the most provocative evidence comes from Russian biologist Alexander Chizhevsky, who documented how historical periods of solar maximum coincided with social upheavals from the French Revolution to 20th century civil rights movements. His controversial Cosmobiology proposed that solar particles might alter neurotransmitter balances, subtly shifting collective behavior. While his methods were flawed, modern research on solar proton events shows they do increase atmospheric nitric oxide, a molecule known to cross the blood-brain barrier and affect mood. We're not talking astrology here, this is about evolutionary biology. For 99.9% of human existence, we lived utterly exposed to the elements, our bodies fine-tuned to environmental cues modern life has largely erased. The real question isn't whether cosmic forces influence us, but how much of that ancient sensitivity remains buried in our genes, quietly syncing with rhythms older than civilization itself. As we peel back these layers, we might discover we're not just inhabitants of the cosmos, we're participants in its grand, invisible symphony. Deep in the control rooms of NASA and ESA, algorithms are learning to predict cosmic events with an almost eerie foresight, not by human programming alone, but by teaching themselves to recognize patterns in data so vast and complex our brains could never process it. These artificial intelligence systems have already revolutionized space weather forecasting, analyzing decades of solar observations to predict violent flares hours before they erupt. In 2022, a machine learning model at the University of Graz accurately forecasted a massive coronal mass ejection 8 hours in advance, enough time for satellite operators to safeguard critical systems. The AI didn't rely on conventional physics models. It spotted subtle magnetic field asymmetries in the sun's surface that human scientists had overlooked, patterns invisible to every telescope until the algorithm connected the dots. But solar flares are just the beginning. At the Asteroid Institute, neural networks sift through petabytes of sky survey data, identifying near-Earth objects years before traditional methods could. Their secret, training on synthetic asteroid orbits until they internalize the gravitational symphony of the solar system, recognizing the telltale signatures of dangerous trajectories amid the noise. One algorithm recently rediscovered a lost asteroid, a space rock observed once in 1991, then vanishing into the void, by extrapolating its path from fragments of data older than the programmers themselves. These systems aren't just faster than humans, they think differently, finding connections between seemingly unrelated variables, like how Jupiter's gravity subtly tweaks asteroid orbits in ways that repeat every 6 decades. The real frontier lies in predicting the unpredictable. At Cambridge's Center for Existential Risk, researchers are feeding AI cosmological simulations spanning billions of virtual years, hoping it will uncover hidden celestial rhythms. Early experiments suggest these systems can anticipate galactic-scale events like when 2 colliding galaxies will trigger a starburst by detecting subtle density waves in interstellar gas. Some theorists speculate that with enough data, AI might one day forecast phenomena we don't even know exist. Quantum fluctuations in black hole horizons, dark matter, tides that shape galaxy formation, or even resonant frequencies between parallel universes. The challenge isn't processing power, it's teaching machines to dream beyond the limits of human imagination. Yet for all their potential, these systems raise profound questions. When an AI at Caltech identified a strange periodicity in fast radio bursts, mysterious cosmic signals from distant galaxies, no known physics could explain the pattern. Was it a glitch, a statistical fluke, or something truly new? Similarly, when machine learning models analyze the cosmic microwave background, they often flag anomalies that defy standard cosmological models. Are these errors, or is the AI sensing the fingerprints of undiscovered dimensions? The irony is rich. We've built tools to decode the universe's rhythms, only to find they might be hearing music we don't yet understand. Perhaps the most poetic possibility is that AI could become a bridge between human and cosmic timescales. While we live decades, the universe operates over eons, its slowest rhythms playing out across millions of years. Machine learning, unshackled from biological lifespans, might detect cycles no human observer could ever witness firsthand, turning ephemeral data points into a symphony of celestial motion. From forecasting supernova to anticipating shifts in dark energy's influence, these digital oracles could transform astronomy from reactive observation into proactive discovery. The universe has always kept time, we're just finally building clocks precise enough to listen. From the quantum realm's flickering particles to the slow, majestic orbits of galaxies, the universe reveals itself not as a static stage but as a living, breathing composition, one where rhythm isn't just a feature but the very foundation of existence. Consider the humble atom, where electrons don't orbit nuclei like planets around a sun, but exist as probability waves, their positions defined by resonant frequencies that dictate chemical bonds and the very structure of matter. Scale up to pulsars, those spinning stellar corpses beaming radiation with the precision of atomic clocks, their rotations so steady they rival our most advanced timekeeping devices. Even black holes, those cosmic vacuums, aren't silent. They ring like bells when they collide, sending gravitational waves rippling through space-time at frequencies we can now measure. This symphony extends beyond the celestial. On Earth, the tides ebb and flow to the moon's gravitational pull, while migratory birds navigate using quantum-entangled molecules in their eyes, a biological compass tuned to the planet's magnetic rhythms. Human bodies, too, are metronomes, Our circadian clocks sync to sunlight, our brainwaves pulse in harmony with Earth's electromagnetic resonances, and even our DNA repair mechanisms follow cycles tied to cosmic radiation levels. The line between us and the cosmos blurs when we realize we're not just observers of these rhythms but participants, our biology and consciousness woven into the same vibrational tapestry. Yet for all we've uncovered, the universe still guards its deepest melodies. Dark matter's gravitational hum remains just beyond our hearing, its particles, if they exist at all, interacting so faintly they've eluded detection for decades. Dark energy's accelerating tempo defies explanation, its mysterious push threatening to drown out all other cosmic notes in a future of infinite silence. And lurking beneath it all is the tantalizing possibility that these rhythms might be signatures of something grander, a multiverse where universes resonate in higher dimensions, or a cyclic cosmology where each Big Bang is a downbeat in an endless composition. What does this mean for us in a universe that operates less like a machine and more like a song? Our search for understanding becomes a kind of listening. Every telescope pointed skyward, every particle detector buried underground, every algorithm sifting through starlight is an attempt to tune into frequencies older than time. The beauty lies not just in the answers we find, but in the questions that keep unfolding. Why do quantum vibrations mirror galactic rotations? Could consciousness itself be a resonance phenomenon, a way for the universe to hear its own music? The more we learn, the clearer it becomes. Reality isn't something we're separate from, it's a dance we're all part of, from the atoms in our bones to the galaxies spinning in the void. So the next time you gaze at the night sky, remember, you're not just looking at stars, you're witnessing a performance billions of years in the making. One where every flicker, every orbit, every pulse is a note in a score we're only beginning to read. The universe isn't playing its symphony for an audience, it's inviting us to join in. And as we keep listening, keep questioning, keep reaching for the next discovery, we're not just exploring the cosmos. We're learning to sing